So we're going to be talking a little bit more about the biomimicry concept, thanks to provide saying Navi. We've already seen some examples of this. We're going to go a little bit deeper into terminology and also what is the role of computational tools when we're designing with biomimicry. So biomimicry is a highly used term, but it might be a little bit confusing because we're talking about bios and mimesis, which is life imitation. But what are we exactly imitating? We go to these terms referring to biomimicry, like we go back to the late 50s, in which biomimicry is first used as the transfer of ideas and analogs from biology to technology. And well, this is a very utilitarian definition of biomimicry itself. And like shape is not very well implied in this. So then we go to the next one, which is which defines biomimicry as a new science that studies nature's models and then imitates or takes inspiration from these designs and processes to solve human problems. We see that this definition makes the concept even broader because we're inserting this inspiration factor, like maybe we do not have to literally copy nature or biology to solve these human problems. And then with this latest definition of biomimicry, we have it is a conceptual approach to seeking sustainable solutions by emulating nature patterns and strategies. And this makes it very interesting because we're talking about two specific features, like first the patterns, which can be related to form and mathematics and geometry in general, and also the strategies which are related to these biological principles that we might use to improve our design. So, what are we exactly imitating or transferring or taking inspiration from or analogizing or emulating? And this is a question that comes up to mind when we're talking about biomimicry. Like, are we copying patterns? Are we copying geometries, forms, strategies, principles, and logics? Something that is not very clear when we first hear this term. So I had this experience when I was at university, when I was in architecture school, and when we started talking about biomimicry, and at first glance, I thought it was something like, okay, so I have to reference some nature shape and try that my project has to resemble it and maybe have certain similarities to it. Then I was kind of bullied for it. So some of the professors actually got to this broader concept of biomimicry in which you can take like biology features and use them to improve your design in different levels. So recently I got this biomimicry like reflection on what is wrong and what is right. So I created this graphic in which we have these two ends. On the left side, we have like the more literal biomimicry, which is like basically the emulation of certain geometries and patterns that we find in nature. And on the right side, we have the total opposite, which goes to emulating biological principles and strategies. So here at this end, we have like a more generic and universal aesthetics. We have like extreme abstraction, like nature language is not too recognizable, but we have this factor that what we are creating here is very optimal, very optimal, and mostly utilitarian as well, because it's based in purely scientific principles. It is very technological, but as we can see, for example, here in the solar panels, it takes inspiration from phototropism, that is very common in nature. But yeah, we see that it totally loses its identity and it doesn't reflect any feature directly as an image from nature. And on the other side, we have like the more literal biomimicry, in which we basically copy the shapes which is called biomorphism. We go more to the literality of things. The images and the visuals are much more recognizable. We tend to go to the sculptural as well as to the identitarian, the representativity and the symbolism. And here at this side, we can say that a cultural aspect takes much more strength. So we have several different biological features that we use for biomimicry, but we might be using for biomimicry. First, we have a first group in which we talk about light and sound response. We have the heliotropism, which is the ability to orient relative to sun to regular exposure, which is seen in sunflowers, algae, and some corals. The phototropism, which is the growth directed toward light sources, which we can see here in plant stems and algae filaments. The negative phototropism, which is growing away from light, which is seen in fungi and also in roots. Then we have this related to navigation and efficiency. We have the path minimization, which is something that we're going to be seeing in the workshop, when organisms find the shortest or most efficient routes, like slime molds and ants. Gradient sensing, movement guided by environmental gradients, bacteria, chemotaxis, and root growth. Also, resource efficiency, where biological growth minimizes energy expenditure. And we can see this in fungal networks and vascular plants. Then we have environmental adaptation, which is something that we're also going to be seeing in this workshop. The adaptive, how skins adapt to climatic data. Like outer layers dynamically regulate heat, light, or moisture, which we can see in reptile skins. Overlapping shielded, that we can see in fish scales, pangolin armor, and pinecone bracts. Layered components protect underlying tissue from radiation or impact. Also, passive thermoregulation, which is the control of temperature without a metabolic expenditure. We can see in these big termite mounds, and also the elephant ears and cactus ribs. And responsive morphology, which is much more visual, which the form changes in reaction to environmental stimuli. For example, pine cones opening and closing, flowers blooming. Then we have relation to the water and fluid dynamics, in which, for example, the fluid guided morphogenesis, which is present in our own bodies, in which the form is shaped basically by the fluid flow forces. You can see in river deltas and vascular systems as the ones that we have as human beings. Then we have, for example, branching networks, which are fractal branching, optimizes distribution collection, like leaf veins, lawns, and rivers. Hydrotropism, which is the growth directed towards moisture sources, which is like the typical route that the roots take when they grow. And capillary transport, which is the passive fluid movement through microstructures. We have light coelyms and most tissues. And then we go to certain principles related to structural growth. We have the adaptive structural deposition, which is the material in which the material accumulates where the stress occurs, and that actually happens in our bones, like bone remodeling, tree growth rings. Minimum material principle, which is mostly present in bird bones and insect exoskeletons, in which structure maximizes strength and minimizes the mass. Stress-driven growth, in which structural form evolves according to the load paths, like structures adapt, for example, to wind forces. Here we have also these coral skeletons. The structural evolution, in which form emerges through iterative adaptation. We can see this in shell growth or skeleton formations. And also anisotropic reinforcement, which means internal fibers align with force direction. It's when we have a section, for example, of a tree. We see how these fibers are modified through time to align to force directions. And structural optimization, which is a very interesting one too, which we talk about material economy, in which you use minimum material to get the maximum performance. We see this in spider webs and bird bones as well. and cellular differentiation, in which cells specialize locally according to function. We start having these gradients in distribution, like gradual variation, for example, the density of a structure, and bone density gradients, feather thicknesses start varying. We see this in plant tissues and in animal skins. So then here come the computational tools that are the ones that help us translate all these principles into feasible data that we can use for modeling and creating and designing in general. So we are placing them in this spectrum that we talked in the beginning, from the more literal to the more technical. So we can find like these two big groups, and I would say that they are very related and almost under the same span. And well, we can say that manual 3D modeling, like for example using Rhino only, we get control over general boundaries. We get control over sculptural features. It might be a little bit more instinctive, and the static identity is based on the manual geometry manipulation. So this one goes a little bit better when it's related to when we start going to this left side, in which we are looking for more of the biomorphism and the literality, or maybe to the sculptural and the cultural as well. And we're going to be using more the algorithmic modeling, where we're going to the left side, to the right side, sorry, in which we are going to be paying more attention to the biological principles and the strategies in general. So here we focus on generative rules. Here we're going to create geometries from zero, taking into consideration these biological principles, and difference with this manual 3D modeling, which we already have defined a very well defined shape. And with the algorithmic modeling, we're going to be context informed. Like we're going to take solar data, water data, wind data, and we're going to start using this information to create new geometries. And the aesthetic identity is going to rely on the algorithmic details. So we do not fall into this like homogeneous languages that we are usually getting when we are working in an algorithmic environment. So I would say that the ideal is to have the usage of these here in the middle, like having the algorithmic modeling, like giving it a very important place in our design, but also taking into account that cultural elements might also appear here and also fit our design. So here is one of the projects that I developed like in 2021, and that's actually when I met Provides in Digital Futures workshop, in which I had a very interesting experience with biomimicry. So we with the team created this kind of shelter for highlands in Peru. Is a place where there's a lot of water scarcity, and the climate is very tough there, and we have a lot of solar potential. So we took inspiration from lichen structures, how they grow towards light, and also how also there are also other structures that are capable of catching humidity in the air and turning it into water. So here we have like these two elements, like the first one, the green one, that is going to be the one that catches radiation and saves it, and the pink one, which is going to be capturing the moisture in the air. Also, we have these spheres in which were assigned because of the because it's a more optimal geometry for getting the most radiation possible from every single direction. So going a little bit deeper into the development of this and the application of computational tools, first we started defining certain random planes and optimizing their direction with Galapagos. And in these panels started tilting depending on where the sun was projecting at certain periods of time and certain periods of times. And so we ran the solar analysis with Ladybug and we started optimizing. So these panels started tilting towards the direction in which they could get the most radiation during this period of time. Also, the shade that these panels produced were analyzed with Ladybug, was projected. And we are actually going to be doing this in the workshop. I've seen that lots of you have already worked with this, so I'm very, very excited to see what you are going to be able to do. And well, once this panel's orientation was defined, we went to Houdini, which at that time was a very good tool for recreating this organic algorithms, and started creating with the shortest path principle, the like having this route and having the target points being these panels, and creating this efficient route to sustain what is going to catch radiation from the sun. So we had this evolution, very, very interesting. We can see this in this picture. Like we had the roots, and then also creating this point cloud, which ended up having this water harvesting device that was also in the design. So we defined like these spheres, which are attached to these panels, to these originally defined structures. And yeah, we ended up with like, sorry. So afterwards, the structure was analyzed once again in Ladybug, and through iterations, we had like different alternatives for variation of the same design in different conditions. And we could reduce the time of processing, because like having this analysis such a complex geometry takes a lot of time. So in this case we used AI to figure out in a faster way what would be like the most optimal variation of this geometry. And well, so we are going to talk a little bit about what we're going to be doing in the workshop in the Grasshopper section. We're going to be reviewing a couple of algorithms which takes biomimicry for the definition. And we're going to be reviewing a navigation, behavior, and response. Navigation, we're going to work with the shortest path growth towards light, which is something which already talked about a little bit before. This is going to be a little bit of the workflow. I'm not going to go deep into this. Right now, we're going to see it tomorrow. We're talking about behavior. We're gonna start defining and designing surface heat tracking growth entities, in this case, related to solar analysis and how they grow towards hot areas. I'm gonna have this type of expression. And solar responsive, of course, we're going to design certain envelopes that are going to adapt to solar orientation based on this analysis that we're going to be running. And also we're going to have some water runoff simulations and how surfaces or volumes influence in this, take part in this, and how they can change the water streams.